I'm now going to talk about using Denevitt-Hartenberg parameters to analyze the kinematics of robots, in particular our 6 degree of freedom one that you're getting for the coursework. And you will recall that Denevitt-Hartenberg uses 4 parameters. And the way Denevitt-Hartenberg is built up is it's basically saying we can represent the transformation from one axis to the next axis, the transformation we need, in terms of 2 screw displacements. So there's going to be a rotation followed by a shift, then a rotation followed by a shift. In fact, the actual order of those is not important, because the way that the Denevitt-Hartenberg is set up, you can actually rotate or translate and rotate. It's actually the same thing in this particular instance. So let's think about the parameters then. So the first parameter is going to be alpha, and basically alpha is the angle which aligns the z-axes together. So if you've got a previous z-axis and the current z-axis, alpha is going to be the angle, right? Alpha is going to be the angle here along the x-axis, right, which aligns the old with the new z-axes. So that's nice and simple. Then we're going to have a translation associated with this part as well. So we're going to have having first of all rotated the z-axes to line up, we then have to move along to see how far they are apart. Also along this, in this particular case, the x-axis here. So we have an A value, which is the length along the common normal, which is the x-axis, corresponding to this translational component. The next part then is going to be accounting for the fact that things might be shifted up and down the z-axis, right? So there could be a point could be up or below where the previous one was along the previous z-axis. So there is a translational component up and down the z-axis by what we call d, this offset. Finally, we have to account for the fact that we can rotate round the previous joint, or joint 1, or joint I in this case, by a certain angle. And this effectively lets us, this is quite often for a revolute system, this is actually the control variable, but basically this is important to align the old and the new x-axes with each other, so we've got to account for this here as well. So just to summarise then, alpha, it's the angle about the common normal, which is the x-axis, which aligns basically the old with the new z-axes. A is the distance between along the common normal, which is the x-axis of these two z-axes. And this represents, in terms of a revolute joint, the radius of rotation around the previous joint. So theta is going to be the angle, basically the control angle in terms of a robot revolute joint around the old z-axis, which is going to effectively align the old and the new x-axes. And d is the shift up and down the x-axis that we have to account for, right? So let's think about doing an analysis again on our simple robot base, so we can compare the results exactly with what we had previously by first principles. Again, we're not going to go through analysing where the Denevitt-Hartenberg coordinates are, we just did that. And we did it also for you in the coursework questions as well, but it follows basically the rules that you have to follow. So first of all, we notice then that the frame 0 is located at the base, and we've got to have the axis of rotation as being Z. So we've got Z0 pointing vertically upwards, because that's how this robot's going to rotate round. And we've got our frame 1 again, and in this case we have to be consistent and have the Z1 going along the axis of rotation. And there's also got to be a correspondence between these two frames, so we can rotate the base frame in order to get frame 1. So the question is, how do we actually do this? We want to find the homogeneous transformation to map between frame 1 to frame 0, sure. And we want to do it now in terms of these parameters from Devenit-Hartenberg. So let's just, again, we're just writing them down here again, just so we can remind ourselves. So alpha is the rotation to align the z-axes. A is the length along the common normal. Theta is going to be the alignment of old and new x. And D is going to be the offset right along the z. So let's think about this. Well, first of all, in order to align the z-axes, we look at frame 0 and we see that the z-axis is pointing up, and in frame 1 we see that the z-axis is coming out of the page. So what do we have to do to z0 to get z1? And if you look at the x0 axis, we see if we rotate positively around x0, and I know it's positive because if you put your thumb in the direction of x0, your fingers, right, are coming round towards you, and that represents the positive rotation. If we go with a 90 degrees positive rotation in that way, then Z0 will rotate round until it's coming out of the page and line up with Z1. So we see, in order to align the direction of Z0 with Z1, we need a positive 90 degree rotation around X, and that is precisely what the alpha parameter is. So we have an alpha value of plus 90 degrees. Right, that's the first one. So what's the next thing to do? Well, what we see is how far apart then, right, are the z-axes? And what we see, actually, is actually the Z0 and Z1 after it's been rotated back, right, are actually separated by 30, right, by the 30 units here, right. This is Z0 to where this is rotated version of this will be is along by 30. So we've got this length along the x-axis, right? The x-axis, the common normal of 30 units, and that's then what we put in the table here. The next thing we can put in, let's put in the D next. So the D is the offset along previous z-axis. So this is the previous z-axis. So what's the offset between this and the rotated version of this? And we see along the axis we have to go 100 units, right? So the 100 units means that D is 100. Finally, we see that we have a final variable theta, and this aligns the two x-axes. So it's going to align x0 with x1. So when theta is 0, like it's written on this drawing, it's written when you do this drawing. I'm drawing this at only one theta value. I can't draw it more than one and one particular drawing. This would be corresponding to 0. But as I turn theta through non-zero values, this would then cause this to rotate round, wouldn't it? This would then start rotating round. So the actual angle which aligns x1 and x0 is going to be theta 1, right? So the final value in the table here is going to be theta 1. So it's easy to compute homogeneous transformations using Matlab. In fact, you can do it by hand, but I do strongly suggest you use Matlab because it's got lots of processing capabilities. It's got symbolic processing capabilities, and it's really it's giving you a way to extend your mind and do the tedious bits for you. And since this is coursework, you might as well, right? If it was an exam, you wouldn't be able to take Matlab in with you, but actually the exams you're going to get, you will be able to, because it's going to be done as coursework. So let's just put, first of all, now in Matlab, let's type in the values that we've got, and then do the analysis that we need. So we've got D is 100 units, we've got A is 30 units, alpha, I haven't got this alpha Greek symbol in Matlab, so I'm just calling it alpha. 90 degrees is pi by 2, right? Positive 90 degrees. Now, because theta, right, is going to be the control variable, I don't want to put in any specific value for it, right? This is something that this is the control variable, and I want it to appear in my equations as a symbolic value. So what we could do is we could build this Denevit-Hartenberg transformation from first principles, right? We can say, let's look right at the bottom first. It's going to be a rotation round x, translation round x, rotation round x, translation along x, rotation round z, translation along z, in that order to come up with this transformation where the rotation around the x-axis is by alpha, the translation along x is by a, the rotation around z is by theta, and the translation along z is by d. Right? So that's basically these are functions that I wrote that give you the homogeneous transformation for a rotation around x, homogeneous transformation for a translation along x, homogeneous transformation for a rotation around z, and homogeneous transformation for translation along z. You can write those yourself. You could also use the values that are in, or the functions which are in Robotics Toolbox as you like, if you wanted to do it this way. Multiply those all out and then evaluate it. So basically, if you did this without the semicolon, it would just print this straight off. And what you see, it comes up with a symbolic representation of what the matrix looks like, but it's evaluated the values, the numeric values you've given it already, right? So it's got the hundreds and the 3 in there, but it's left the theta as a symbolic variable because we called it a symbolic variable. So this gives you the formula that you need, right, in order to do that. And you'll see that is actually the same as we had previously when we did the values by hand. So you should print this out, well, copy it and show, when you're doing this kind of analysis, compare that, what you've got there, with what you had before. There's an easier way of doing it than doing it from first principles in terms of screw transformations. You could also just put the values in, put your symbolic theta in because that's what we need. You could also directly use the formula, right? There is a formula for a Denevit-Hartenberg transformation, and this is the formula in terms of theta, in terms of alpha, in terms of a, and in terms of d. So you put your values in, you could directly then evaluate that. And again, you'll come up with, well, provided you haven't made any mistakes, you'll get exactly the same result. So that's another way you could do it directly. There is a third way, and you can use Robotics Toolbox. So you put your values in again, like this, right? We then, basically, you build a single link, right? And do look into the help on the Robotics Toolbox. So link is a command to build a link. It's normally used to build all the links in a robotic arm. I'm just building a single link corresponding to this particular frame that I'm analysing. I'm calling it now R1, so it's robot 1, a 1 degree of freedom robot. I'm then building a serial link. So this is my link of robotic linkages. I've only got one in there though, right? So it's just going to give you one. I'm then setting, right, my angle. So I'm putting the default configuration in. So I'm just setting my angle just to my symbolic theta because I want to know what the forward kinematics are going to be when I've got a value theta. But theta is symbolic and Matlab can handle that. And then all you need to do is to get the forward kinematics is just call the, well, after you've built your serial link, you call the member function fkine with the basically the control variable in there that you want to use, which is actually theta. And what it'll do is it will calculate the overall forward kinematics. Now, in this case, it's just calculating the overall forward kinematics for a single joint, right? So it'll calculate that for you. And again, that should be exactly the same you've had by all the other methods, and you can compare that with what you got from the other methods, including the direct method, if you wish to do so. So you're being asked specifically then to analyse this 6 degree of freedom arm using classical Denevitt-Hartenberg. So in other words, what I'm asking you to do, I've given you the frames, so there shouldn't be any confusion there. You've just got to fill in the table, right? You've got to fill in the table. Have a look at the example already that I just gave you, and it shouldn't be too difficult to come up with the values. Another nice thing about doing the analysis by hand first, right, the first principle ones, is you should always, when you actually evaluate what the corresponding homogeneous transformations are, they should all be the same as you got previously. And if something isn't the same, somewhere you've probably made a mistake, right? So I'm just breaking it down for you again, so you can just see what you've got to do. First of all, you've got to analyze Denevitt-Hartenberg for frame 1. So, what are these values for frame 1? What are these values for frame 2? Again, I've just put in the next frame. What are these values for frame 3? What are these values for frame 4? And so on, or link 4, and links up to link 6, in fact. So, as we know, the overall transformation that arises then from the Denevitt-Hartenberg is the product of these 4 basic transformations. You can actually put them in by hand if you want to. You can use the forward kinematics commands in Matlab and what have you. Basically, this is what it comes down to. This is the formula. This is the formula I've also showed you in Matlab. So you can directly type things in to this formula in order to get the Denevitt-Hartenberg homogeneous transformation for a particular link. And the idea that is you can then compare what you got directly in the first part by direct analysis to what you got maybe using the matrix like this, but certainly you could also compare it with what you get using Robotics Toolbox, which does most of the work for you. I've already showed you how to do that.